Hi there and welcome back. On today's video, let us look at the production and manufacturing of vinyl chloride. I would like to credit a textbook by the name of Process Design by Sider and also an article from ATSDR. They have a nice article that is very informative on vinyl chloride. Today's aim, it is to achieve a very high concentration, at least 90-something% of vinyl chloride. We will not be focusing much on the scale. Why vinyl chloride? Let us assume there is a need to manufacture it, which is a very important industrial chemical briefly used to produce polymer, polyvinyl chloride. It is always important to consider the future generation and their well-being. They should not be affected by any activities or actions that we partake in today, and therefore, with that being said, environmental considerations need to be incorporated into any engineering design that is done or conducted. Since we'll be designing vinyl chloride, it is important also to note that it is extremely toxic, and therefore industrial plants that manufacture it or process it must be designed carefully to satisfy government health and regulations. What is vinyl chloride? Vinyl chloride, also called chloroethene, ethylene monochloride, or monochloride ethylene, also vinyl chloride monomer. It is a petroleum-derived chemical, I guess, with a sweet odor at room temperature. It is a manufactured chemical and does not exist naturally. Vinyl chloride is a chemical intermediate and not a final product. Hence, vinyl chloride is often fed into a polymerization, converted from its monomeric structure to form a polyvinyl chloride. Its uses, it is used to manufacture polyvinyl chloride. Smaller amounts of vinyl chloride are also used and found in furniture, automotive parts, and was previously used as a refrigerant. Be sure to check out our carbon dioxide used as a refrigerant to cool down water. Okay, now moving along. Health-wise, breathing a high level of vinyl chloride, depending on the dosage and also a period of time, can impact one's health. It can impact the lungs, liver, and kidneys. As for polyvinyl chloride, it is used to make a variety of plastic products, including pipes, wire cable, coatings, and also some packaging materials. Since we'll be working on a simulation, it's important to consider certain factors for vinyl chloride. This includes at room temperature, it is a colorless gas and burns easily, but at high pressure, still at low temperature, it can exist as a liquid form. Liquid vinyl chloride can evaporate easily, and it is not stable at high temperatures. In most cases, a design engineer would assess various routes for producing vinyl chloride using various factors such as Gibbs energy, profit, inherent safety index, potential environment index, and atom economy. If you check out the product and design textbook, you'll notice that they've already assessed various routes that can be used to achieve vinyl chloride and also found the most sustainable route. There is more than one way to manufacture vinyl chloride. The first way is using direct chlorination of ethylene. For this route, you add ethene and chloride to give you vinyl chloride and hydrochloric acid. It is said that it occurs spontaneously at a few hundred degrees Celsius, but unfortunately does not give a high yield of vinyl chloride without simultaneously producing a large amount of byproduct, which is something we're trying to avoid. The second route that one can follow is by adding acetylene with hydrochloric acid to give you vinyl chloride. For this route, it was determined that a good conversion of 98% of acetylene to vinyl chloride was achieved at 150 degrees in the presence of mercuric chloride catalyst. For the first step, you would react ethene with chlorine to give you dichloroethane. The next step would be to crack down that dichloroethane at high temperatures because it is an endothermic reaction which will result in vinyl chloride and hydrochloric acid. This reaction, it is a two-step reaction. The first reaction, which is 4.3, is exothermic reaction and produces a lot of heat. For the second reaction, which is 4.4, this route was determined to be endothermic and occurs spontaneously at 500 degrees. Reaction part 3, which is thermal cracking of dichloroethane from chlorination of ethylene, was the selected route since it is the most profitable. So we are going to take all this knowledge that we are given here and try and convert it into a simulation using Coco. If you have Asepn Plus, that would be awesome. Okay, now that we've selected our desired route, let us start with our simulation. I am going to use Coco. I've already added my property packages and my reaction packages. I have 3 reactions here. I have the first reaction, which is the first step, whereby we'll be adding chlorine and and ethene to give us dichloroethane. The next step, which is to crack the dichloroethane to yield vinyl chloride and hydrochloric acid. Now to achieve this, to add chlorine and ethene, to mix them together, we can use a unit mixer and have two streams, which is chlorine and ethene at different flow rates. This can be mixed together and fed into our Gibbs reactor. The temperature here is set high. Even in the reactor, it can take place at least at 75 degrees to yield a very great strong concentration of dichloroethane, at least 99%, which is really good. Now the next step will be to preheat our dichloroethane to prepare it for a high temperature it should expect to react at in the Gibbs reactor. Now the Gibbs reactor, second reactor, will help us crack down the dichloroethane to yield a very good 50-50% ratio of vinyl chloride and hydrochloric acid. Since the temperature took place here at a super high temperature of at least 200 degrees, we are going to want to cool it down using a heater cooler before we feed it into the next step of our process, whereby we are going to use 2 distillation columns to separate everything. We now have a cool down stream of vinyl chloride plus hydrochloric acid. This can be fed now into 2 distillation columns. To achieve this, we are going to have a second mixer. The reason is because we are going to have a recycled stream from the second distillation column. This can be mixed together with this stream to feed into the first distillation column. Our distillation columns are going to operate at different pressures. The first distillation column will operate at a low pressure, at least 2 bar, and the second distillation column can operate at a high pressure, at least 12 bar. Now you'll notice that the pressure difference here variates a lot. To try and minimize this, we can have a pump and a valve to control the pressure difference from the first distillation column into the feed that goes into the second distillation column. The first distillation column is going to separate hydrochloric acid. Unfortunately, we didn't separate a lot of it. We just have 74%. The aim is always to have a high concentration as possible, but good news, if you go into the second distillation column, we can separate that which we want to achieve, which is 98% of vinyl chloride. And at the bottom of the second distillation column, we have dichloroethane, at least 100% of it, or 99.9999%, and small traces of other chemicals such as chlorine can be spotted there. This bottom stream can be mixed into the second stream together with the feed of the Gibbs reactor number 2. This was an interesting simulation to look into, and remember we said vinyl chloride, it is not a final product, it is an intermediate which can be used to now produce polyvinyl chloride. Till next time, bye.